So in the previous lecture, I introduced what are the real analytic functions, and then we also saw some basic properties of one basic property of power series, that is the convergence. The set of convergence is an interval. Okay. So how did we define the real analytic function? So I said real analytic functions are the functions where the function is equals to its power series. Its power series, I mean to say that so this is the meaning of, okay, so if this holds, okay, in an interval, say mod x minus x naught is less than r, then we say f is real analytic. You can say real analytic at x naught or near x naught, okay, because the power series converges in an interval, so it converges at all points in the interval, right? So around any point you can write the power series. Therefore, you can write either real analytic at the point x naught or around the point x naught. Okay. So you see that this is the Taylor series. So let me briefly recall how we get the Taylor series. Okay, so it is from the Taylor's theorem. So what the Taylor's theorem says, that you can write the function f(x) as say k equals to 0 to m of fk x naught by factorial k into x minus x naught power k, plus you have a remainder term Rn plus 1. Here this Rn plus 1 is going to be f m plus 1 at a point which is, say, let me write theta x plus 1 minus theta into x naught, at a point which is lying between x and x naught, okay, divided by m plus 1 factorial, okay, into x minus x naught over n plus 1, where this 0 is less than theta less than 1. So this is how the remainder term looks like. Okay. So in the case of real analytic functions, this remainder term is becoming 0. That is, as m tends to infinity, we get all the terms here in the series, and you can write this as Rm. So Rm depends on m, Rm plus 1. So Rm plus 1 goes to 0 in case of when there exists a series, when the series converges to the function. Okay, so that is the real analytic function. This is one way. The other one is that you write the series. Once you have to first thing is that you have to check this remainder term goes to 0. So that's where you get the convergence of the pointwise convergence of this the validity of the series, and then you can use the power series methods to check the convergence of the power series in a positive radius of convergence. Okay, so this is briefly about real analytic functions. So how to identify this real analytic functions? So there is no trivial way. So you need a theorem for the complex analysis, which we reduce to our real case. So it says the following. So these are real analytic functions are quite different from the complex analytic functions, because in case of complex analytic functions, if the function is differentiable at a point and it's in neighborhood, you have the function is going to be analytic. Once if the function is analytic, you can write the Taylor series expansion. That is, Taylor series expansion is valid. Or in other words, if you write the Taylor series expansion of the function, and if you check the convergence of that, then that has to be equal to the function. Okay, so that is the thing that you get in case of complex analytic functions, but that's not the case here in the real case. Okay, so I will just tell you what is the sufficient condition. Of course, it is also necessary that you can easily derive that, the necessary condition. But my interest is to look at the sufficient condition, that is to identify how we identify the real analytic functions. Okay. So it says the two conditions: f is a real analytic, at a point say x equals to a. And second statement is for every interval containing a, I mean to say interval is a small interval, not all the intervals we take, because the function may not be real analytic in the entire real line. So we take any small intervals around the point a. Okay. There exists the constant c greater than 0 and r greater than 0, such that the derivatives, get the derivative of this x is going to be less than or equals to constant c factorial k by r power k. Okay, and this holds for all x in the interval. So let me write this side. So for all x in I. Okay, so this is one is if and only if 2. So 1 implies 2 is not our concern, but 2 implies 1 is our concern. So that gives the sufficient. Okay, so then consider these two statements. Okay, so we can write let 1 and 2, and then you have 1 if and only if 2. That is, if 2 is satisfied, then it becomes a real analytic function. Okay. So why is that? You look at the what I said previously, the Taylor's theorem, and look at its remainder term. Okay. So what is the remainder term? It's going to be mod, if I take, it's going to be mod of fn plus 1 by m plus 1 factorial into mod x minus x naught. Right, so I write 2m plus 1. So this is mod. So all of you can watch the videos, but you don't have to become busy in writing the things, because I'm going to share the notes. Anyway, we'll have also the videos. Yeah. So this is going to be less than or equals to the constant times mod x minus a power n plus 1 and fn plus 1 of the point psi by n plus 1 factorial. This constant is not there. So this is the remainder term. So this is we have that estimate that says that this is going to be less than or equals to c into mod x minus a power n plus 1, and this is going to be n plus 1 factorial by r power n plus 1. That's what we have, the estimate on this term, and 1 upon n plus 1 factorial. So these things gets cancelled, and you will have the c into mod x minus a by r over n plus 1. Okay, so this now you see that this goes to 0 if mod x minus a is less than r, strictly less than r. Okay, if mod x minus a is strictly less than r. So this r is and the small interval around the point a. So this shows that this Rn plus 1 goes to 0. Okay, therefore the validity of the Taylor series is there. Okay, so once you have this, then you say that the Taylor series of the function is equal to the function value. Okay. On the other hand, one can also use the root test. I leave this as an exercise to you, but I am yet to do the root test. we can also use the root test to show the convergence. To show the convergence of the series, okay? Convergence of Taylor series. But remember that this you have to do this Rn plus 1 goes to 0 for saying that the function is equal to that from the Taylor's theorem. Okay, so this is the sufficient condition. So we need certain things from the power series. I already said one principle that one initial thing that we proved is was that if the power series converges at any point other than the center, okay, then the radius, then the set of points where it converges is going to be an interval. Okay, if it converges only at the center, then it's only a singleton point. Otherwise, it is going to be an interval. So another result that we require is the radius of convergence formula itself. Okay, so if any of you have difficulty in understanding any of the terms that I am defining here, please ask me. So don't assume and don't tell me later that we didn't know what these elements are. You can disturb me now and ask me. There's no urgency for completing the syllabus for me or doing anything else other than making you understand the idea of differential equations. Okay, so we consider the series an x power n. Okay. So we write, suppose beta is the limits period of nth root of mod a, or we write this is mod an power 1 by n. Okay, so this is mod an power 1 by n. So this is another notation used is lim sup is like this. Okay, this is also the same notation. So then we define if the limit is okay, then and r equals to 1 by beta. Okay, so this 1 by beta, if beta is 0, r is infinity. Okay, so this is with the convention that it's going to be infinity if beta is 0, and if beta is infinity, it is going to be 0. Okay, and it is going to be 1 by beta if beta is finite. With this convention, then the series an x power n converges, you can say converges or converges absolutely. Okay, converges absolutely for mod x less than r. For mod x less than r. Okay, so this is what we require, but what happens for mod x greater than r, we can show that it diverges. Okay, so the diverges, and mod x equals to r is something which the test doesn't so right. So these are all the things which you probably are aware of. So let me ask you once again, if any of you have difficulty in understanding any of these things, please let me know. Okay, so this is one thing, and this is called the nth root test. Nth root test. So if the
another root,
yeah, yes
सर इस रूट टेस्ट के अंदर तो हम 1 से कंपेयर करते हैं ना कि कन्वर्ज होने के लिए मोड एक्स लेस देन 1 और ग्रेटर देन 1 के लिए जब लिमिट अप्लाई करते हैं तो 1 से छोटा आएगा तो कन्वर्जेंट होगा, ग्रेटर होगा तो डाइवर्जेंट होगा, उससे कंपेयर करते हैं ना हम.
No, that is for the series, right? This is for the power series.
Okay, sir.
Yeah, that is for the series. Okay, let me tell you what the for the series, right? So series, if I take an, the series of numbers, and then you look at the lim sup of mod an, okay, power 1 by n. So call this as maybe alpha. So this is if alpha is less than 1, series converges. Absolutely. So if alpha is greater than 1, the series. Yes.
The Cauchy-Hadamard theorem.
What?
Cauchy-Hadamard theorem.
Cauchy.
Convergence of series.
सर कोची रूट टेस्ट बोलते हैं जैसे कोची रूट.
Yeah. So most of the calculus is by the Cauchy only. So whether we write Cauchy's root test or nth root test, it's basically the root test. Basically look at this.
Okay, sir.
Right. So this basically comes from here. What I am writing there. If I take an equals to, you take an equals to an into x power n. Okay. And then you look at this, then you get mod x, whatever I said. Okay. Whatever the test is, then you get from here. Okay, the conclusions of this nth root test follows from here. So what is the an important thing that we note here is if the limit of this remark, if the limit of mod a n power 1 by n exists, okay, then beta may be written as limit n tends to infinity of mod a n plus 1 by a n. So this is normally called as a ratio test. Okay, but for that the limit here should exist. Okay, so this limit should exist. If the limit exists, then only these two things are equal. Otherwise, they are not. Otherwise, they are not. Okay, so this is also known as the root test. Sorry, not root test, ratio test. Okay, so this is about the convergence, or we say that this R is the radius of convergence. Okay, R is called radius of convergence. Okay, R is called the radius of convergence. In that interval, the series actually converges. Okay, so this is about the convergence of, remember that we will use, in case the limit exists, limit of this game exists, then we use a n plus 1 by a n also. Okay. Another thing what I require for differential equations is, some of you might have seen the method of power series. That is when you take a series and then differentiate term by term. Okay. So that is another important thing that we require is, can I differentiate a power series term by term? Okay. Suppose I write fx, a function which is defined as an to x power n. Okay. So unless I mention, if I write a sum like this, then it is always from n equals to 0 to infinity. Then what we can say is, say this is true in mod x less than r. That is, the series converges absolutely for mod x less than r. Then say that f is differentiable in mod x less than r within its radius of convergence. Okay. And its derivative, f prime of x, is going to be an n to x power n minus 1. So we can see here for n equals to 0, you can write, but n equals to 0, it becomes 0, because here in the series also it is a naught. A naught is a constant, so the derivative of that is 0. So you can write this from n equals to 1 to infinity. And this validity of the series is also going to be mod x less than r. So there are two things that we are saying here. That is, the power series is differentiable, and moreover, I can write the derivative of the power series by differentiating the series term by term. Okay. So it's easy, as if you assume this conclusion, it's easy to apply, but let us see how a proof of this comes. Okay. So one can show that the series in F prime converges, okay, has the same radius of convergence as the series in F. Okay, so that is the thing, that is the limits of k, ak. These are the coefficients here. Okay, power 1 by k. So k power 1 by k goes to 1. Therefore, this is going to be the lim sup of mod ak power 1 by k. And we know that this is equals to r. Okay, because the power series converges. F converges in R. Therefore, the series in F prime, or let me write the series a n x power n minus 1 converges for mod x.
Excuse me, sir.
Yeah.
So this should be equal to 1 by r.
Yeah, 1 by r. Thank you. It is going to be 1 by r. Therefore, the series converges for mod x less than r. The series. But we have not yet shown that this is the derivative of f. So how do we say that the function is differentiable? The function is differentiable. For differentiability, we have to compute what is f of x plus h minus fx on h and its limit, right? So we will show that minus f prime x, okay, and its limit. We show that this is going to be 0. Okay, so this is what we claim. Then this shows that f is differentiable and derivative of f is equals to f prime. F prime, I mean to say that the series that I wrote there. Or if you want for clarity, you can take that series as g and then write it as g here. Then finally we say that the limit exists, then g is nothing but f prime, the derivative of f. Okay, so what is this this factor? Okay, so f of x plus h minus fx upon h minus f prime x. So this is going to be look at f of x plus h minus fx. When you subtract this, the constant term goes away. Okay, the constant term goes away. So it will have the from the a1. Okay. Right. So a1 into the first term. Let me write only the first two terms to tell you that actually the a0 plus a1 into x plus h. This is the thing. Okay. And you subtract a0 minus a1x like this, minus this is one thing divided by 1 upon h, okay, minus f prime. So f prime is going to be a1 minus 2a2, okay, so minus 2a2x like this. So if you see here, a0 and a0 goes away, and a1x also gets cancelled. Okay, with this. Okay. And h is here, h and h also will get cancelled, and therefore you have a1 and a1 also gets cancelled here. So as a result, you get a series like this. The series starts from n equals to 2 to infinity, okay, an to this is x plus h power n minus x power n on h minus n x power n minus 1. So we have to see how this series behaves as h goes to 0. Okay. So for this I have a less space, so I cannot refer to equations again and again. So can remember this, I guess. So I take an identity. Okay, so let us recall an identity. So the proof of this identity is not very difficult. You can prove this by induction. I leave this again for you to prove. It's very simple induction. You can use on this. So this is equals to a power n minus 1 plus a power n minus 2 to be a b power n minus 2 plus b power n minus 1. Okay, and so this is proof is by induction. So I leave this as an exercise to you. Try. Before I share the notes, one can try this. Okay, so I take this and differentiate this with respect to b. Differentiate with respect to the variable b. Then we get the following formula: a power n minus b power n minus n b power n minus 1 into a minus b upon a minus b whole square is equals to a power n minus 2 plus 2 times a power n minus 3 into b plus n minus 1 into b power n minus 2. So in this relation, we take a equals to x plus h and b equals to x. And then we assume that mod x plus h is going to be less than r as h goes to 0, right? That's what we eventually take, right, as h goes to 0. And anyway, mod x is also less than r. Then we see what I'm going to get here. So if I apply this inequality, I get x plus h power n minus x power n. Okay, that is a equals to x plus h and b equals to x minus n into x power n minus 1 into the difference of these two, that is nothing but h. Okay. So the absolute value of this, that is going to be, there is a minus b whole square, that is going to be the h square. A minus b square is going to be h square. Okay, so this is equals to x plus h power n minus 2 plus 2 into x plus h power n minus 3 x plus n minus 1 into b power n minus 2. This is what we get. So when I take the absolute value in all this, so we can write this is less than or equals to, right? So mod x plus h is less than or equals to less than r, and right, so everything is going to be less than this is less than r power n minus 2 and less than r power n minus 2. Everything is less than r power n minus 2, right? Right, so this is going to be less than or equals to r power n minus 2. So where I take big R, small r is less than big R. Any small r less than big R. Right, so r power n minus 2. You can take big R also, there's no problem here. Into what you have, the first term is 1 and this is 2 and up to n minus 1. So you know the sum of the first n minus 1 terms in an arithmetic progression. Right, so this is going to be less than or equals to n into n minus 1, okay, n into n minus 1 into r power n minus 2. So I don't have much space on my tablet, but this is how the calculation. I'm not missing any steps here. So therefore, this is what we have. The left hand side is the one we have in the previous page, that is here. Okay, so now let me take that calculation to this f of x plus h minus f of x by h. And so that is mod f of x plus h minus f x by h minus f prime. And so this is going to be less than or equals to the series n equals to 2 to infinity of mod an. Okay, and the factor that we have as the big one, x plus h power n minus x power n minus, right, x plus h power n minus x power n minus n x power n minus 1 into h on h. So this is, we know that this is less than or equals to, we saw that this is going to be less than or equals to mod h, okay, times the series n equals to 2 to infinity times mod an into n into n minus 1 into r power n minus 2. So now you can see that since the series converges, okay, so this series also will converge. This one is a convergent series for any r less than r. Okay, so you can take, because the radius of convergence is going to be bigger, so this converges for any r less than r. So apply the ratio test or root test. Ratio or root test. This series is going to converge for this thing. So this is something which is now a finite number. Okay, so this is mod h into some constant, which is the limit of the series. This is the limit of the series, above series. Okay, so if I take limit h goes to 0, this goes to 0. So therefore, limit h goes to 0 of this thing is going to be 0. Okay, so this is how we show that the series is differentiable. The infinite series is differentiable, and the derivative of infinite series is going to be the term by term series of the given series. Okay, so another result that we require is this one. So if I take a series a n x power n equals to 0, okay, then 0, I mean to say, with some positive radius of convergence, then the an equals to 0 for all n. So you can see easily that by taking x equals to 0, you get a naught is 0, right? So take x equals to 0. This implies that the series a n x power n is nothing but a naught, which is 0. Okay. So to get the a1, we can differentiate the series. So differentiate the series. When I differentiate the series, I get a1 plus right 2a2x and so on. Take again x equals to 0 plus a1 is 0. Okay, so differentiate the series means this is equals to 0 from the differentiate this relation. We say series of this relation, differentiate this relation. So repeat this to get an is 0 for all. Okay. Okay, so any questions?
No, sir.
No,
No
sir.
questions. Okay, good. So let me take a very simple equation and then let us start doing the things and then see where we have the difficulties. Real analytic solutions. So let me start with a very simple equation, that is y double prime equals to y, and you all know the solutions of this equation. Here the sign and there, sorry, you know the solutions, right? So e power x and e power minus x. Of course, you can write. So you can compute the solution for this. So I'm not going to repeat this trivial calculations, but you can do that. So let me take an example which is slightly non-trivial. So take an example where my y double prime minus 2x into y prime plus 2y. So this is a second order linear differential equation with the variable coefficients. Okay. So let us assume yx is a solution in this form. Okay. With some positive radius of convergence. We don't know as of now whether there is any function or whether we can find ANs in such a way that the series will have a positive radius of convergence. But we assume this. We assume that this is true for mod x less than r, and therefore we can differentiate it and then substitute in the equation. Okay. So we can differentiate it y prime. We can differentiate it. Y prime is going to be the series n an into x power n, and you can
X power n
x power n
minus
minus
1.
1. Yeah. So you can write x into y prime. So this is becomes n an into x power n. Right. So you can write similarly y double prime is n minus 1 n into x power n minus 2. Okay. So we substitute this in the given equation. Okay. So we get k equals to 0 to infinity of k plus 2. You can write k or n because it's only an index, so you can write anything. K plus 1. So write a k plus 2 minus 2k ak plus 2ak. So this is what we get equals to 0. And then we can apply the previous theorem, what I said, that the series is going to be 0 in a positive radius of convergence, then all the coefficients are 0. Okay, so this implies that you get a relation that is a k plus 2 is equals to 2 into k minus 1 upon k plus 2 into k plus 1 ak. Okay. So we can take now k equals to 0. So this is true for k equals to 0, 1, 2. So take k equals to 0. I get 2 times a2 plus 2 times a0 is 0. So this implies that a2 is equals to minus a1. It means a0. Okay. So take the other equation, that is k equals to 1. Okay. So this implies that a3 is 0. Right. So 0 times a1, which is 0. So once if a3 is 0, use the recurrency relation here to show that a2k plus 1 is going to be 0 for all k. Okay, so that is all the numbered coefficients are going to be 0. Okay, and even number coefficients you can compute using these coefficients. So how the solution looks like? So you write the solution yx, which is a1x plus a0 into all the coefficients we can write x power 4 by 6. Right, so we got the series here, and there is a simple polynomial here. So x is one solution. So this is what we write a1 phi 1 plus a0 phi 2. Okay, phi 1 and phi 2 are two linearly independent solutions. So the linearly independentness is not difficult to show. That's very simple because x, one side it is x, which is not a constant multiple of the series like that. But for the convergence of the series, so if you see the coefficients of the series that are coming here, they are first one is A0, second one is A2 and A4 like that. So the series A0, A2, A4, A6 like this. So they are related by this recurrence relation. Okay, they are related by this recurrence relation. So from the recurrence relation, so you can write this as A0, A2, A4, or you can write this as B0 and this as B1, B2, B3 like this. And then you can write mod Bn plus 1 by Bn. Right? So it's going to be the same as the AK plus 2 by AK plus 1. AK plus 2 by AK. So that's how they are related, right? These are the adjacent coefficients. So that is going to be less than or equals to 2 into K minus 1 upon K plus 2 into K plus 1. So you see that this is now going to be 0 as limit exists as K tends to infinity. Therefore, by ratio test, okay, the series converges. By ratio test, the series converges. Converges for what? For all or for all x. Therefore, converges for all x. So it's fine, well and good. So we have a simple equation, okay, a simple equation like this, and then we could write the power series, and then we could use the term by term differentiation. We got a recursive relation or recurrence relation, and from that recurrence relation we found two linearly independent solutions and could easily check the convergence. Now suppose I have an equation like this. I have an equation y double prime plus e power x to y equals to 0. Okay, so in this case, how do I apply the method? I take the series y in the series, and exponential of x also has a series, and then I have to multiply these two series. Okay, so that is we have a series an x power n, and you will have another series coming from exponential. Okay, so let me write that as maybe alpha k x power k, or alpha n x power n is the same index. Okay, so I have to multiply these two things, and then I need to get this in the form of again a series, right? So because y double prime will be in the form of an into n minus 1 and x power n minus 1. So I need something in the form of x power n. So such a product of the series is called the Cauchy product. Okay, so such a product of the series is called the Cauchy product. So we need to know, when given two series like this, if they converge in a positive radius of convergence, in an interval with positive radius of convergence, then can I multiply the series like this and then get a series in the form of, again, looks like a polynomial, right? So nth partial sums are polynomial. So when I multiply two series, I should get the nth partial sum to be polynomial. There are different types of products that you can take, right? But for the power series, this looks more natural because it's like polynomials. You have a nth partial sum of first series is a polynomial, and the second series is also polynomial. So you multiply these two nth partial sums and then get a series, and that is the series which is called the Cauchy product. Okay, so what does the Cauchy say in this case is you can write the product of two series, which is ak x power k multiply this by series Vk over K. Okay, so you can write this as the series, okay, say Ck exponent. Okay, Ck exponent. So this is the product of two series, where this Ck is like, you know, take two polynomials. So if I take two polynomials, say a0 plus a1x, okay, multiply this by say b0 plus b1x. So what do I get? There is a constants, right? So you get a0 b0. This is a constant, plus you get a0 b1, right, into x, plus b0 a1 into x, right? So like that you will get terms which are of this type. So the Cauchy product is also the same. So Ck here, so the Ck is write n equals to 0 to k, an p k minus 1. So that's how the Cauchy product looks like. And the theorem says that if the series ak x power k and ek x power k converges in mod x less than r, then the series ck x power k converges for mod x less than r. I mean, it only says it converges for mod x less than r, but the convergence, the radius of convergence for the product can be more than this r. Okay, so this r is the minimum. For example, this r is the minimum. For example, I can take the function f(x), which is 1 plus x on 1 minus x. So this has a power series. You can write the power series expansion of this in mod x less than 1. Similarly, you write the function gx, which is 1 minus x by 1 plus x. Okay, so when I take the product of these two things, this is going to be 1, right? So this has the product converges for all, but whereas this one converges only for mod x less than 1. Okay, so the product convergence, the radius of convergence is the minimum that you get, not the maximum. Okay, so today the time is close to, so I will stop it here. I'll continue tomorrow, the product of the series and then a general theorem of convergence. Do you have any questions quickly?
Excuse me, sir.
Yes.
Sir, in the first question, whereby you were telling about real analytic solutions,
Yeah.
can you please flip that page? Y double dash minus 2xy dash plus 2y. Yes, sir, this one. So next page. Sir, hereby you have written that k plus 2 into k plus 1 into a to the power, this is k plus 2 into x to the power k. But sir, we have y double dash. We are not having x square y double dash.
Oh,
so,
well, you have to, I thought you people know the technique of adjusting the terms. So let me tell you how to do that. See, you have here the y double prime. So let me do at the end maybe. So you have to say, for example, if I take y, which is the sum an x power n, right? So I write y prime as the sum n an x power n minus 1. If you see that this actually series is from n equals to 1 to infinity, right? So if you expand this a little bit more, I get a1 into x, right? a1x plus a1 plus a2x. So what I will do here, I want to write this as n minus 1 as n itself. So you write, you take k equals to n minus 1. And then what happens to the series here? So n becomes now k plus 1. Okay, and an becomes a k plus 1. And n minus 1 here becomes x power k. Right? And n equals to 1, therefore k equals to 0 to infinity. And k is only a dummy variable, right? So this is same as k is a dummy variable. So I can write n equals to 0 to infinity, n plus 1 into an plus 1 into x power n. Because k is only a dummy variable. It's only indexing. That's not really playing any role in the series other than use it for index. So similarly, we can do the same thing for y double prime also. We can do the
Right,
same
sir.
thing.
Got that. Thank you, sir.
Right? Yeah. Okay. Any other questions?
No, sir.
Okay. So if you have no questions, let me break it here. We will continue in the next class. Thank you.
Thank you, sir.